So good morning, everyone. So welcome to the KLESF STEM webinars on the energy storage as an options of complementing renewable energies. So in these webinars, we will share about the use of energy storage as an options of complementing renewable energy for sustainability and environmental conservations. It will cover the latest on the renewable energy storage technology, and new generation batteries. So the webinars will divide into the following parts. So first, we will share on the latest on renewable energy, the energy storage systems to complement renewable energy, and lastly, the energy storage and new generations. So today, the speaker will be me, Dr. Chong, Assistant Professor with the Departments of Electrical and Electronics Engineering of Lee Kong Chian Faculty of Engineering and Science, University of Tunku Abdul Rahman, and Dr. Jun Hian Kiat, Associate Professor with Departments of Mechanicals and Material Engineering with Lee Kong Chian Faculty of Engineering and Science, University of Tunku Abdul Rahman. So let me first invite Dr. Jun, who has an area of expertise in energy storage, renewable energy, solar cell materials and fabrication, as well as solution process solar cell to share about the contents for these webinars. Please, Dr. Jun, the floor is yours.
All right, thank you, Dr. Chong. Let me know if my voice is not audible.
Sure, thank you.
Okay, good morning, everyone. So the topics for today's webinar is concerning the energy storage as an option, or I would rather say interesting option in complementing all the renewable energy sources, right? So before we talk more about the concept of energy storage, I will brief the audience on the little bit background, like why we choose renewable energy and what's the reason behind. So let me start sharing my screen. All right, please let me know if you're not able to see anything in the moment. Should be able to see my first slide.
Is everything okay?
All right. Okay, so my surname is Jun. Just a brief introduction. So I currently attached to the Department of Mechanical and Material Engineering, the Lee Kong Chian Faculty of Engineering and Science. Okay. So I think most of the audience are from Utah, but for the benefit of non-Utah audience, just a brief introduction. University Tunku Abdul Rahman, basically we have two campuses. We have city campus in Sungai Long, which is quite near in Kuala Lumpur, and then the main campus in Kampar, right? So I attached to the city campus, and so as Dr. Chong, right? Okay, so the outline of my introduction for the first half of the session, I will cover on the global issues. Okay, then I will move on to the renewable energy in Malaysia, specifically in Malaysia. Okay, and from there, I will pick one of the technology to give a brief review. Okay, so I will talk about the solar energy in slightly more details. And finally, we will look at the issue and solution. How does this issue link to the energy storage? Right, so I think everyone knows about the global issue currently. Is the hot topics that the newspaper or even the broadcast, okay, is reporting on the greenhouse gas emission. Okay, so I have this slide showing the breakdowns on the different types of greenhouse gas emission. Okay, not necessarily coming from carbon dioxide or CO2. Of course, CO2 form the largest chunk of the gas emission contribution. But more or less, we have other types like methane, like nitrogen oxide, and even fluorinated gas coming from the air conditioner system. So knowing that CO2 contribute about 65%, basically more than half. Okay, it is coming from majority of fossil fuel and industrial processes. So a lot of action needed if you want to reduce this CO2 emission. Okay, So that the question is, why do we need to reduce the CO2 gas emission? If you look at the trend of the CO2 emission for the past 30 years, I would say 30 years, starting from 1980s, we have incremental rate of the CO2 emission. As you can see that on the left side of the graph, right? And then when we break down in terms of the contribution, okay, CO2 contribution by the fossil fuel, we can safely say that, okay, coal, oil, and gas contribute the most. Okay, with majority coming from the coal. There's no surprise to see that there's a drop of the CO2 emission last year, particularly due to the COVID pandemic, when most of the industrial has reduced their processes. So that's why you get this reduction of CO2 emission. But moving forward, okay, if everything back to the normal, we can safely say that the CO2 will continue to be on the positive side of the chart. All right, so one of the solution of reducing the CO2, okay, basically is to replace the consumption of fossil fuel. So how do we do that? We can use alternative energy resource like renewable energy, but how far are we in getting all this fossil fuel technology being replaced by renewable energy? If you look at the chart on the left side, it's basically not much. Just last year, okay, but still very good. Okay, we can see that it's almost achieving 30% of the global electricity generation, which is derived from renewable energies. Okay, so when this type into the big picture, we can see that there will be change or shift in the power sector emissions, okay, as an effect of the energy mix of the renewable energy. So on the right side, okay, you can see that is again the CO2 contribution. Okay, you will see that the positive contribution mostly coming due to the electricity demand. Okay, that's where our power generation cater for, just to meet for the electricity demands. Okay, so we need to offset this, okay, by introducing a mix of renewable energy. Nuclear is not in picture here. I mean, it's not in the consideration in Malaysia, okay, not even in ASEAN, but in developed country, they are still one of the options, okay, because of the low cost. Although it invites many criticisms and also environmental impact concern. Okay, so this slide would give us some snapshot on where is our trend for the CO2 emission in the next 10 years or a few years later. So we are right here, okay, so this is last year data, 2020, okay. We know that our CO2 is somewhere between 31 to 32 gigaton CO2 emission. If we have a very good sustainable recovery plan taking place, okay, the emission rates for the CO2 will drop, okay. But without any action, okay, it will go up, okay, as expected. So we can foresee that it will not go to the yellow region. I foresee that somewhere between the white region and the green region, okay. Let's have to look how aggressive each of the countries look into their sustainable energy. I mean, their renewable energy implementation. Okay, so because of the CO2 emission, we have climate change issue, and that's where the Paris Climate Agreement come into the picture. This Paris Agreement, I would say that most of the countries have already signed. Okay, Malaysia is part of the signatory countries. It was signed in 22nd April 2016. So why do we sign this Paris Agreement? Okay, it's one of the efforts to reduce the CO2 emission. Okay, So if we compare with our neighboring countries, each of our neighboring countries like Thailand, Philippines, and Indonesia, they already set up their targets, how much CO2 emission they will need to cut for the certain period of time. So for Malaysia, okay, a few months ago or maybe last year, okay, the target was like 25% of CO2 emission, okay. So the key points from the Paris Agreement is the reduction of the global temperature increment. Okay, the target is to not have more than 20, no, not more than 2 degrees Celsius. Okay, so that's the ultimate objective, as you can see that from the point number 1. I think everyone knows about this one. We have the latest 12 Malaysia plan, whereby one of the strategy is to have a sustainable socio-economic growth. So how can we achieve this? Several ideas like introducing carbon pricing and carbon tax. Probably some of you have heard it. Okay, that has been proposed, okay, as a way to mitigate the CO2 emission. Okay. Apart from that, okay, the target, okay, which I mentioned just now, 25% of renewable energy mix, okay, which has been planned for 2025, it has been revised upwards to 31%. So this is, I would say, rather ambitious, okay, but it's a good target point, okay. Other than that, by 2050, okay, Malaysia should become a carbon neutral nation, okay, carbon neutral nation. Beyond 2050, probably will be carbon negative. Okay, that's what we hope for. So this is on the recent global issue and local issue. So the reduction of carbon emission, I picked one of the global company, Shell Oil and Gas. As we know that Shell company, they actually focus in the fossil fuel like petrol and diesel and gas. Okay, but they realize that, okay, moving forwards in the next century, fossil fuel may not be the main contributor for the energy consumption. So they already set up some plan, okay, to shift from the fossil fuel technology to new technology. So I use new technology because they proposed in the year 2010, somewhere within there. New energy can be consist of a variety options of energy source. So if you look at the proposal of the Shell company, they call it blue sky scenarios. Okay, they actually embark on various types of exploration of a new technology, specifically on the renewable energy. So as you can see that from this graphic, we have wind energy and of course solar PV. Okay, and other than that, they also put more emphasis on the hydrogen. Okay, so come to the end of the century, okay, hydrogen should be form at least 10% of the final energy consumption. Okay, so this is what that company is focusing and expected to carry on some of the interesting activities. So that is on the global. Moving back to our homeland in Malaysia, where is our renewable energy status? How does it differ from years to years? I have the data points, okay, charting from year 2012 to 2019. Okay, you can see that the ratio, okay, or the energy mix coming from the renewable energy or RE has been increasing, okay, from year to year. For the past 10 years, the increment is about 12%. Okay, so majority coming from the solar PV. Okay, the rest are from hydro, okay, and biogas. Okay, we have more than 50% coming from hydro. As you know that our country has I would say that good flow of river, especially in Sarawak, okay, and even in the west coast of Malaysia. Okay, so Bakun Dam being the biggest dam in Malaysia has played a huge contribution to the energy mix of our country. All right, so let's see. Okay, so what are the types of renewable energy that has been implemented in Malaysia? There are three currently that Malaysia has adopted. Of course, everyone knows about the solar PV. So solar PV means photovoltaic. And then we have hydroelectric, okay, and biomass. These are the three main renewable energy technologies that has been adopted and applied in Malaysia. We do not have wind energy, okay, because we do not have regular wind pattern, okay. Hydrogen we have not started except at a trial scale in Sarawak, okay, in Kuching. So these are the three that we should have focused now. All right, so what are some examples of the solar PV that has been put in place? I picked a few examples in reference to this book. Okay, we have solar farm in Kudat, Mukim Tanjung in Sungai Siput. Okay, and then hydroelectric, we have a lot of examples. Okay, the best known example is Bakun Hydropower Dam, okay, in Sarawak. So if you haven't been there, I think it is worthwhile to have a visit. I actually been there myself a couple of years ago. It's a huge project, an interesting place to get to know how the electricity being generated. We have the same state of Sarawak, Burung, then Pegau and Kenyir. So Kenyir is in Peninsula here. And what about the biomass? So biomass, because Malaysia is heavily dependent on the palm oil, okay, palm oil industry. So we have a lot of biomass coming from palm oil. So you can find that most of the biomass plants are actually within or beside the palm oil plantation. For example, like plantation in Sabah, okay, and then we have a few in Peninsula, okay, which I did not show it here. So why do we need to choose renewable energy? Okay, as I explained, because of the global issue of the climate change, there is a need, okay, to move from fossil fuel consumption to new energy technology. Okay, so is there anything wrong with the fossil fuel consumption? Basically, will be the high rates of CO2 emission. That's what give us the global warming and climate change, right? Other than that, we have a haze, toxicity of gases, okay, acid rain effect, particulate matter that will affect the health of all the population. So we have these scenarios that has been suggested by Swiss Institute. Okay, if everyone or every country in the world, okay, able to play their roles, we can achieve the reduction of temperature increase there, okay, as enshrined in the Paris target. All right. So how can we translate it into economy? With the reduction of CO2, okay, of course, we have better health, okay, and what the institute has suggested or expect, okay, there will be some economic contribution, okay, from the reduction of the temperature. All right, some examples of the energy mix. So this data is coming from the United States, okay. We know that we can safely compare Malaysia and United States. The ratio for renewable energy basically is less than 50%. Okay, in US it's like less than 10%. In Malaysia, if you remember from my previous slide, I think also somewhere less than 20%, where we're going to achieve 25%. Okay, so a few more years later, hopefully can get 31% or 30%. So by and large, similar to Malaysia, okay, mostly from solar, okay, hydro, and biowaste. Okay, the types of renewable energy that we have now, which is in mature technology like solar PV, wind, hydroelectric, geothermal, biomass, and ocean. Okay, So geothermal, not, I mean, basically we don't have geothermal power plant. We used to have one in Sabah, it's in Tower. I think that project didn't went well. Okay, so we don't have geothermal. Okay, ocean technology, like wave and tidal, probably we have a very small scale for research basis. And there is one team in UTM. They're working on the OTEC. Okay, so this OTEC power plant, they have proposed to install it at the west coast of Sabah. Okay, somewhere near the Island. All right. So I'll pick one of the technology, okay, to introduce, okay, how does this renewable energy, okay, generate electricity. So I'll pick on the solar PV. This is where my research interest in, okay. All right, by comparison, okay, worldwide, solar PV has been the main contributor for the energy mix, okay. So what is the solar cell technology or solar PV technology that we are using now? Most of the household, okay, solar panel that you have, like you can see on the rooftop that has been installed, are basically coming from the first generation solar PV. So what are they? So they are the earliest solar PV technology being introduced, okay, by using the silicon materials. So silicon materials, if we purify it, we can fabricate it in terms of either monocrystalline or polycrystalline. So this is just a different names how to classify the types of silicon materials within the solar PV. So by and large, the efficiency for solar PV first generation, 20% more or less. Okay, some of them are able to get like 25%, but depends on the brand. Then we have the second generation solar PV. It's thin film types. Okay, we have cadmium telluride, okay, and CIGS. Not so popular here, I would say that, but we do have a few factories manufacturing second generation solar cell, right? Thin film solar cell. And the latest technology will be the third generation. So these are the new materials or novel materials that has been used to fabricate the solar PV. Okay, so still at research base, most of them, but there are few companies overseas. They have come out with the commercial products using the third generation solar cell. All right. So how do we quantify the performance of the solar cell? We use the efficiency. Mean, let's say the solar PV receive like 100 units of solar light. Okay, from this 100 unit, how many units will be used to convert into electricity? So that kind of ratio that we use to calculate in terms of efficiency. All right, so this is one of the charts. It's very comprehensive charts. Okay, if you look at the legend, we have the silicon solar cell shown in purple and dark blue. And then we have the second generation solar cell, okay, in green, and emerging PV will be the third generation solar cell. Okay, so because the first generation solar cell has already matured, you can see that. I mean, you can see from this chart, their efficiency is quite high. Okay, it's basically above 25%. The latest data that we have. Thin film also catching up, okay, so as the emerging PV. So emerging PV, like perovskite types of solar cell, they started 10 years ago, more than 10 years ago, but they have a lot of improvement, okay, which is now, okay, on par with the thin films. All right, so just focus in on the emerging PV. You can see that there are lots of different technology of third generation solar cell that has been researched. Okay, so the graph that I show here is lab size cells. Okay, so when we want to introduce into the commercial market, we need to test it in terms of module. So this is where the module efficiency plot come into the picture. So if you look at the imaging PV, okay, in terms of module, okay, already that Panasonic and a few companies have already started to be able to produce very convincing performance, okay. So the size is still small module, okay, but small module size or even standard module size, okay, is actually sufficient for our household usage or even for the IoT consumer devices usage. Talking about the IoT device, Exodus is a startup company in Europe. Okay, they have already introduced the integration of the third generation solar cell with the IoT device. So as you can see from on this slide, wireless headphone, okay, which you do not need to charge. Okay, so what happened here is there's a strip of solar cell, okay, being integrated into this earphone. So basically, you do not need to charge your headphone, and basically you can use it for the whole day. Another product that the company has introduced is the helmet, basically cycling helmet. You may ask why do we need solar cell put into the helmet? So well, basically you have to know that if you are a cyclist, a good helmet should have like the light indicator at the back of the helmet. Okay, so that's where we need energy. I mean, that's why we need the electricity to be used, okay, to light up. Okay. All right. Fundamentally, how does the solar cell works? I have this simple diagram. Okay. So basically, solar cell. I take example of silicon solar cell. We have a layer. Okay. When the light strikes onto the materials, okay, certain parts of the materials, I mean the atoms or molecule, they will receive sufficient energy for them to release the electron. So this is the electron whereby it will move to the one end. Okay, so when the electron being moved out, we create hole. Okay, so the hole will move to the other side. So the electron will ultimately move out to the external circuit. Okay, so this is where we get the electricity. Just a brief concept. But third generation solar cells are slightly different in terms of the working mechanism. Okay, still rely on the electron being produced, but what's so different is how that electron being produced. I pick one example is the quantum dot or QD, whereby the electron is being released by the QD materials itself. Okay, the previous slide was the silicon. Okay, so silicon is in crystal form. Okay, so it's a slightly different phase or different physical entity. Okay, if you compare the silicon QD. Okay, so how can we quantify the performance? We use this formula. Okay. Basically, what we need to get the response in terms of the current density and the wattages of the solar cell when they're working on. So when we have the renewable energy put into place, there will be some opportunities that we can tap or explore in the next few years or maybe next 10 years. So two of the opportunities that Malaysia should look into. One is hydrogen energy. Basically, we have, I mean, the Malaysian government has already have some policy on the hydrogen energy. The next will be the multi-generation system. Probably very new terms, but maybe some of you have already heard it. It's like, for example, like combined cycle power plant, or we call it cogeneration, which we have already started that kind of power plant, whereby instead of using the single output, we have two outputs that can contribute to the useful production of electricity. So that is where we should look into it. All right, so we have opportunity. Of course, we also have challenges. Take, for example, the solar PV that I have explained just now. What are the issues and challenges? Of course, the solar PV only works when you have sunlight. So if it is cloudy, you will have intermittent power generation. So you probably won't be able to get a very stable power output. Okay, and sometimes you may get excess power generated because your demand may be lower than the supply, and at some point maybe the power supply is insufficient because your demand is higher. So how can we solve this issue? One of the solutions is to integrate the energy storage system with the solar PV. Okay, so energy storage should not necessarily able to be integrated with the solar PV. It can also can be formed as part of the whole system with other type of renewable energy system. Okay, so it'll be very interesting energy storage, not necessarily at the macro devices, but it can also play a very important in the miniature devices. So I will pass to Dr. Chong, okay, to explain more on the energy storage system. Okay.
Thank you, Dr. Jun.
Yeah. Okay, over to you, Dr. Chong.
All right, let me share the screen.
So just a brief introduction about Dr. Chong. He's an assistant professor at the same faculty as mine. Okay, he attached with electrical and electronic engineering department. Okay, he has passion, or I would say that he has expertise in renewable energy power system, hybrid energy storage system, electrical power system, and even machine learning for the electrical demand forecasting. And last but not least will be the IoT for the electrical power system. Okay, so Dr. Chong will introduce more about the energy storage because this is his field. All right, over to you, Dr.
Thank you, Dr. Jun. So good morning, everyone. So very interesting sharing by Dr. Jun just now. So to the audience, so if you have any question you want to ask regarding my presentations or Dr. Jun's presentations, please feel free to type in the chat box, and then we will answer your questions by the end of after the presentations. All right. So Dr. Chun actually threw out a few questions by the end of his presentations. So the challenge that we are facing right now with the renewable energy power system, particularly the intermittence of renewable energy outputs, and then the over generations, excessive power, and lastly would be the okay. So now let's look at the outline for my presentation. So today I'm going to cover the challenges of integrating renewable energy with the grids. The grid that we're referring is the electricity grids that we have in our countries. Okay, for examples. Then I will go through some energy storage technologies, the new generation batteries. So what's the hype about the new generation batteries? And lastly would be the hybrid energy storage systems. So what would be the challenge if we integrate renewable energy with the grids? So it has something to do with a duct. Okay, so how does it relate to this duct? Okay, let's find out. So in 2013, the utility service provider in California, the California Independent System Operator, published a chart. So this is the chart. Okay, so you can see in this chart is over 24 hours, the average energy demands over 24 hours in 21st March in 2013, where you can see that these are the peoples in the regions. Okay, from 1 a.m. then people are sleeping. So you can see the load is rather constant. Okay, and then you will start seeing that people in California waking up, the energy demands actually rising, and then they go to work. Okay, rather constant. And then during the night time, around here, people going back homes, switching on their lights, their fans, everything. You can see that the load is rising, right? So over the night, and then they go to sleep again. So this is the patterns of the peoples in California, how they consume the electricities. And usually for the operator of the energy service providers, so they will anticipate the usage. They anticipate this usage, and then they will plan their generations to fulfill this requirement, these load requirements. Okay, as it's rather easy to forecast because it is quite stable throughout the day. So the utility manager might find it, all right, so no issue. So we can fulfill that. But things get interesting when we have more and more PV system installed in our electricity grids. So let's look at the next year. It's 2014, okay? We can see that the load is rather constant during the midnight, okay? So, and then it starts increasing when people waking up, okay? This one is more obvious as compared to 2013. Again, the same things. You see, during this afternoon period, it should be quite constant, right? But we start seeing a dips over here. Okay, a dips over here. This is due to the installations of rather small portion of PV system in the grid system. And during this period, around from 7 to all the way to 6, the PV start generating powers. So therefore, we see a little bit drops over here, a little dips here. Okay, and then when the sun goes down, you will see that people start turning on their lights, fans, everything. So the load goes up again. Okay, and then go to the night. And then the next year, 2015, we see that, okay, it's rather constant, rather similar to 2014 in terms of mornings, okay, going up. And then you can start seeing the dip is getting deeper. Okay, in fact, it's lower than 2013 now. Okay, and then going down during the daytime when the sun shines. So over here, and then when the sun goes down, then the energy start increasing again. And 2015 and 2016. So again, you will see the similar trend during the morning time. Okay, morning time. When the sun comes up, the dip in the energy demands. So remember, this is the energy that the utility service provider, the power plant, need to generate to supply the loads. Okay, so we can see that during the midday, the utility service provider, the power plant, do not need to generate as much as energy as compared to 2013 because the increasing installation of the PV. So it dip again, and then it goes up when the sun goes down. Again, similar patterns. In 2017, it's even more obvious. The dip after the sun comes out, okay, it go way below 2013. Again, the same patterns. This is 2018. So again, we find that rather similar patterns. And in 2019, you can see that the dip is quite huge, okay? It's quite huge. So by now, do you see a patterns of a duck? Okay, so this graph is generally known as a duck curve, okay? The California duck curve. So where this is the duck tail, so where people are sleeping and start waking up, and then this part will be the duck belly, okay? Generally from around 7 to 5 or 6 p.m. to 6 p.m. Okay, so this is the duck belly. And then this will be the duck head when the sun goes down. So by looking at this graph, we can see that the nutritions from the PV actually making the belly of the duck getting bigger and bigger. So the PV is so nutritious, and we'll start having this duck curve appearing. Okay, so what would be the challenge to the utility manager when this happens? Okay, so obviously, let's look at the 2019 curve here. So in the morning, you'll see that there is a sharp slopes over here. So where you as a utility service provider, you will need to ramp up your generations during the daytime when people start waking up and the sun had yet to come up. Okay, so this looks right. The service provider will need to supply that. And then when the sun comes out, so the needs from the energy from the power plant actually drops. Okay, so the power plant will need to reduce their generations. Okay, so they need to reduce it, scale it down, and then when the sun is out, and then when the suns go down around these regions, okay, around this region, you'll find that there will be a sudden increase of ramp. Okay, from here all the way to here. In just 3 hours, the generation plant need to ramp up their generation by about 13,435 megawatts in just 3 hours of time. So then the power plant will need to hurry up, so quickly boost up their generations to fulfill these energy requirements. Okay, so there is a challenge to them. This ramping up is expensive. okay? And because of this drop in the belly, okay? So remember, this drop is subject to the weather condition as well. What if you have a rainy days or cloudy days? So the drop will not be as deep as compared to when you have a sunny days, right? So the operator cannot totally shut down their power plant. So the power plant will still need to idle. So in case there are any drops in the PV system, they can quickly generate electricity to supply the grids. So the ramping up and the stop-start, they cannot stop, okay? So the stop-start, it will be expensive and not very familiar to the operator of fossil fuel power plant, okay? So what if the sun, the PV plant, we install more and more PV plant? You will see that more nutrition, the belly will get bigger, okay? So when the solar energy generate too much and the PV plant, the fossil power plant cannot turn off. So when too much energy from the PV flow into the grid is what we call over generations. It will actually affect the stability and it might as well damage the grids. So this is the problems that we are facing when we have too much of generations during the afternoon time. Okay, and here is the challenge. So what would be the existing solution to this, the duct bellies? Okay, so this is what we usually the operator will do, is called the curtailments of renewable energy. So we know that the grid operator is trying their best to match, to fulfill to supply the sufficient energy to the demands of our areas. Okay, so when the PV energy or renewable energy is too high, we have no choice because we cannot turn off the power plant. So we have to reduce the output from the PV. Okay, so if you can look at this graph, so this is also in California. So you can see that for every month, this is the amount of energy that we are generating, okay, from the PV systems. So if you look at the gray color ones, supposedly, if we let the PV panel to run at full powers to generate the maximum power that can output, you can see a larger curve like this, okay, during the day. But because it will have a risk of overloading the grids, so no choice, we have to curtail the renewable energy outputs. So the gray color one, the highlighted in gray colors, is the energy that we lost by curtailing the renewable energy outputs. So because we need to reduce the outputs. So this one, supposedly we can generate it, but for the stabilities of the grid, we have to sacrifice this part of the generations. Okay, so if you look at the graph here, you can find that the monthly curtailments by California from 2015 to July 2021, as we install more and more power system, you can see that the amount of energy that we curtail, the curtailments, solar curtailments, the energy that we lost is a lot. Okay, we're getting more and more energy being go into dummy somewhere without any use, right? So we wasted this much of energy. So another problems with the grids, right, is actually the picker plants. Okay, so natural picker plants operate infrequently. So if you see, we have a power system, a power plant over here, fossil fuel power plants. You have the utility grids and supply to the loads. So what happens out of sudden, for example, in summers or certain crises, we have higher load demands. Okay, we have significantly more load demands. So the power plant will not be able to supply that much of powers. So what it will actually do is that we will turn on a picker plant. So generally, the picker plant is always sleeping. Okay, it's only being turned on when there is a need, there is a surge in the peak demands. So it operates infrequently. It's only at the time of peak demands in order to balance the grids. And to run this picker plant is high cost and also inefficient, because as we've seen just now, the power plant, the fossil power plant is known to be operate on and off. Okay, it should run consistently. So this is inefficient. And then another interesting report by the Bloomberg this year. Okay, over here you can see that in 2020, So it actually analyzed the LCOE. It's called the levelized cost of electricity. So how much is the cost to generate the energy, okay? Dollar per megawatts. What is the price to generate 1 megawatts of the energy? And we can see that, let's look at the PV first. You can see back in 2019, we can see that the PV price is going down significantly. So this thanks to China. So because of their mass productions of the PV panel, the price actually drops a lot faster. Okay, and then over here we can start see somehow it gets slower now from 2016 to 2020, and then we have the onshore wind farms, wind generations. So it's also going down the price. So for the time before 2018, the battery storage, okay, is actually quite expensive. You can see the curve is rather quite high compared to the others. So therefore, the battery storage was not very common back in 2018 or even before that. So, but according to these Bloomberg and the research companies, so it shows that the levelized cost of electricity for battery is actually dropped from around $300 per megawatt hours to $150 in just 2 years of time. Basically, it has dropped about 50% in just 2 years' time. And if you look at the PV is dropped from second half of 2019. It's about 4% drop in the PV price. And then the offshore wind energy is about, the onshore wind energy is about 9%, but the battery is 50%. So at this point, the research company actually says that the new built battery can be competitive on the cost with gas pickup plants. So now it will be more reasonable and much more cost effective to build a battery storage instead of a pickup plants. Okay, so we can actually replace the pickup plants with a battery storage. So we store the energy. So when there is a peak demand, we can use the energy from the battery to supply the peak demand, as well as we can, if we have the PV system installed, so we can use this battery to solve the dark valley issue as well. So, and we can soon phase out all the pickup plants in coming decades. So now let's look at what is the energy storage system. So I do not use the terms battery. So we all are very familiar with the term batteries. So, but to be more precise, battery is one of the energy storage systems. So the energy storage system is the system of converting electric energy from power system into a form that we can store. Okay, we can store and convert it back to electric energy when needed. Okay, so it's just like a bottles. Okay, so imagine that you go to restaurants where they have a free flow of drinks. You can have a bottle to fill up the drinks and drink it anytime you want. Okay, so in order for you all to understand the performance metrics of energy storage system, I will first introduce a few terms. Okay, so the first one being the energy density. So the unit is in watt per liters, is watt hours. It's watt hours per liter. Sorry, I messed up the units. It's watt hour per volumes. So watt hour is the energy. Okay, so if you can see that as a stamina, the higher the watt hours, the more stamina you have. You can run longer without feeling tired. Okay, you can travel longer distance. All right. So the next one would be the power density. So power is power per volumes. So the power is watt per liters. So don't confuse with power and energy. Energy is the stamina, how long you can run. The power is at the particular point of time, how much power you can produce is strength. What is the load you can lift? Okay, so that is the strength, the power. So one is about how much we can deliver in a short time. One is how long we can sustain for a long period. It's the stamina and the strength. So the next one would be the cycle life. So a battery can be charged from 0 to 100% and then we use it back to 0. So this is about 1 cycle. This is what we call the cycle life. So one full cycle and one recharge is called 1 cycle. So the battery, for example, they actually have labels of how many cycle life they can cycle for how many times. Okay, so it's like the bottle, how many times you can refill. So lastly, it would be the service life. It's a useful life in years. When the engineers that design the battery, they will put in a design life. So this battery is supposed to use for maybe 10 years or 5 years. Okay, so this is a few parameters that we can see. So in terms of energy storage technologies, we can see that this is why I don't call the energy storage system as battery, because the energy can be stored in many different forms. It can be magnetics. Okay, it's a SMAS, superconducting magnetic energy storage. Kinetics is the flywheels. So electricals is supercapacitors, and the one that we've seen a lot will be the electrochemicals. It's lead acid, lithium ion, and then sodium sulfur and flow batteries. Okay, so we store the energy in the electrochemicals form, and lastly will be the chemicals. So we stored it in a hydrogen form. So it's a hydrogen storage system. But the most common one would be the electrochemicals. So now I show you, after you know the energy and power density, let's look at this plot called the Ragon plots. Okay, so basically this plot rates all the energy technologies that we have in the markets right now. So the power density, remember how much power we can deliver. Okay, how strong is it? The energy, how good is the stamina? So we can see that here, the battery, lithium-ion, for example, lithium-ion battery has high energy density. So in a smaller size, it can run longer, for example. So it can contain much energy in smaller size. And when you look at the power density, as we go higher, that means in, let's say, 1 liters, it can deliver much higher power. So if you look at this, as we go towards this direction of the graph, okay, as the energy storage technology located on the top right corner, that means it can deliver higher power and higher energy in a smaller size. That result is decreasing in the storage volumes. And then on this side, it will be increased storage volume. So it's desired to have the technologies over here because they can deliver much higher power and higher energy in a smaller size. It's lighter. Okay, so we can see that. But one very important thing we find is that there's not single energy storage system that is high in both sides. Okay, this is somewhere in the middle. So we do not find somewhere around here. So let's look at types of batteries. Okay, so the battery is actually the key technologies for decarbonizations for the power and also the transport sectors. So this is a lead acid battery. It's commonly used in automobile, in your car. The PV system is a well-established and mature technology. We can find that the cost is relatively low, but the problem with the lead acid battery, this is a very long, really old technologies already. So the cycle life is about 500 to 1,000, and the service is about 5 to 10 years. It's not as good, but let's put it next to the lithium-ion batteries. So this is actually the most popular battery right now that you can see in the markets. So it has a high power density, significantly higher than the lead acid battery, and then higher energy density as compared to this. So higher cycle life and also higher service life compared to the lead acid battery. So that this actually means that the lithium-ion battery can actually store much more energy in the smaller volumes. Okay, but the cons would be it's much more expensive as compared to the lead acid battery. So what are the applications of lead acid battery? So all of you will be very familiar with Tesla. Okay, so you commonly find the lithium-ion battery. So this is the Tesla gigafactories. So where this factory actually produce the battery cells, the lithium-ion battery cells for Tesla's products, such as the electric vehicles. And then they have this power wall for residential use energy storage, and also the utility grid systems. Okay, so these are a few different applications. So one interesting news about the batteries in the grids, right? It will be the installation of mega battery in Australia by Tesla back in 2017. So in 2017, severe weather in South Australia actually caused the states to have power outage. And then there was the ideas in the Twitter where someone asked Elon Musk, okay, about whether if he's serious to help Australia to solve the power outage. And then Mr. Musk actually replied yes. And then he is saying that if the battery is not built within 100 days, then the state will receive it for free. So, and then the Tesla went ahead and built the battery grid storage for South Australia, and it actually get it done within 60 days. Okay, so it's rated about 100 megawatts, 129 megawatt hours, integrated with a wind farm. And back in 2017, it was the largest grid storage, battery storage at that time. It can also power 30,000 homes without any issues. So another ones would be Tesla also telling that the nickel-rich Indonesia that they want to set up a plant in Indonesia, because Indonesia has a very rich nickels, which is the raw materials for producing lithium-ion batteries. So this is an overview. Who are the major manufacturers of lithium-ion battery? So the largest one would be the LG Chem, the CATL, Panasonic, SDI, Samsung, and the rest. So what is the problem with lithium-ion battery? So this is the structures, a cell of the lithium-ion battery. So this is one cell of it. So usually in the lithium-ion cell, we have multiple cells in it. So it consists of anodes, cathodes, separators, and then we have liquid electrolytes. Okay, so during the charging process, the lithium ions, okay, will extract from the charging process, right? We plug in the charger. So the lithium ions will actually flow through the separators and intercalated with the anode materials. So the lithium ion will go to here. Okay. So when the reverse process, then the electrons will discharge and then discharge to hit electrons, and the lithium ion will go back to the cathodes through the separator. So this is the process of charging and discharging of the lithium-ion batteries. So what is the problem with lithium-ion batteries? So the first one, for us, we will still find that this charging time is slow. For an EV, you might take 40 minutes to charge the car. Okay, and then every time you charge it, there will be a capacity loss. So now you can hold 1,000 watt hours. After you charge for few cycles, it might drop to 98, 95. Okay, 95%. So it has also safety concerns. So if we exposed to temperature variations, the battery was swollen. Okay, so if we exposed to mechanical stress, or if we puncture the battery, because it has a highly flammable liquid electrolytes in it, so when the separator is punctured, it can lead to fire. Okay, so in fact, another battery storage in Australia by Tesla was caught in fire in July 2021, a few months ago. So they are still investigating what is the issue. So let's look at the next generation battery. So we know that these are the issues that we want to solve, right? So we want to have faster charging time, good capacity retentions, and also less safety concerns. So that comes to the next generation battery. So this is the regular plot that we've seen. Now I add in a new components. It is a lead metal battery, okay? Or we call it solid state battery. So this solid state battery has significantly higher specific energy and specific power. So higher energy density and higher power densities as compared to lithium ion battery. So if you look at a report from QuantumScape, this is the lead acid battery that we've seen earlier. This is the lithium ion battery, and we're looking about energy density, the stamina, okay? The stamina in a smaller, in the same size. So solid state lithium metals can actually hold much more energy as compared to the others. So a smaller size, but it can hold much more energy. So basically, the solid state battery is a battery technology that uses solid state electrodes and solid state electrolyte instead of liquid polymer gel electrolyte found in lithium ion. So we can see that the lithium electrolyte in the conventional lithium ion is flammables, but in lithium metals, so the electrolyte is solid and is not flammable. Okay, because we are using the lithium metal anodes, which has a higher specific capacity as compared to the graphite. So basically, the specific capacity is 10 times higher than the graphite. So that means it can hold significantly much more energy as compared to the conventional solid state batteries. So the operation will be quite similar to the traditional one, just the material and also the electrolyte is different for lithium metal, but it can achieve much more better performance compared to the others. So let's look at what are the players in the markets to develop in developing the solid state battery. So the first one, for example, would be the quantum scale. It's a battery startup backed up by Bill Gates and also Volkswagen. So now in December 2020, they actually reported that the battery can travel longer range than the conventional lithium-ion battery by 80%, and it can charge from 0 to 80% in just 15 minutes, and it has a very minimal capacity loss. Okay, every time you charge and discharge, so it will not lose the capacity as fast as the conventional batteries. So they target to produce all this battery by 2025. The other players will be Toyota. So Toyota this year it will try to debut a game-changing solid-state battery for a SUV model. Okay, so he also reported that it can travel extra 300 miles of range than conventional battery. So it can charge 0 to 100% in 10 minutes with minimal safety constants. And it still can retain 80% of the capacity after 800 cycles. But similarly, we can only see this product. This is just a debut only and just a prototypes. We will see the solid state coming out by around 2025. And coincidentally, we can see that the timeline is 2025. Okay, so now the solid state battery actually overcome the drawback that we mentioned earlier about the lithium battery. It has faster charging time, good capacity retention, and safe. But what stopped it from being boom in the market right now? Okay, so this is because they are still in the research and development stage. Okay, so the cost of producing it is still high. Okay, so we will expect the mass production in 2025. So with mass productions, the cost will be much more affordable, right? And then we can start seeing much more and more solid state battery coming into the markets. And there's still some technical things that need to be refined before mass productions. So there's something that we can look forward to. Okay. So the last concept of energy storage is an interesting concept called the hybrid energy storage system. As we've seen earlier, none of the energy storage technology is high in both sides, correct? Energy or power. So there are some research going on to combine two different energy storage systems with complemented characteristics. So for example, a battery is somewhere around here, the acid battery. So it has high energy density, low power density, and low cycle life. And then we can combine it with a supercapacitors. So this is somewhere high over here. Okay, so the capacitors has low energy density, but it has high power density and high cycle life. So if we combine them together, you have an all-rounders energy storage system that is high in both energy and power density and also the cycle life. And then there's another project in the UK. It's called the Energy Superhub Oxford. So Energy Superhub Oxford will install the UK first transmission connected hybrid batteries. Okay, so it basically uses the lithium-ion battery around here, lithium-ion battery. It has high energy density, high power density, okay, and low cycle life. And we combine it with the vanadium flow battery. So which is around here, this is the vanadium flow batteries. So it has low energy, low power, and high cycle life. By combining them, they can actually take the advantage of both storage in their operations. So for example, the flow battery, because it has very high cycle life, it will not degrade that much. So it supplies the base load, and the lithium ion will supply the peak loads. So by doing this, we are getting the best person to do the right job, and we can maximize the potential of each of them. All right. So that's all from my side. So I hope that give you some ideas about the energy storage in renewable energy. Thank you.
Yeah, thank you, Dr. Chong.
Thank you. All right.
Okay, so yeah. So let's conclude our presentation. Okay, so we'll move forward to the question and answer. I believe we have a few questions.
Yes, I have a few questions. So to the audience, please feel free to type in your questions in the chat box, okay? But we have received a few questions before the sections. All right, so the first questions is actually asking what is the initial cost, maintenance cost, and its lifespan for energy storage systems. Okay, so this is an interesting question because we have different technologies, right? We have the electrochemicals, we have the electricals, the magnetics, the kinetics, energy storage systems. But this one, the most common one would be the lithium-ion battery. Okay, the most common types of energy storage system in the market would be the batteries, lithium battery or the lead-acid battery. So when we try to employ this kind of systems in our grids or your homes, your factories, there are a few costs that we need to consider. So the first one will be the capital cost. Okay, so what is the upfront payments that we need to pay, how to buy the batteries, and then we need to buy some converters to convert the DC energy from the battery into AC so you can use it in your house, and then some infrastructure as well. So some construction. So you can see that the cost per kilowatt is about 271. Okay, it's a little bit more costly than the lead-acid battery. So we have the price for the converters. So the total project cost is about $1,876 per kilowatt and $469 per kilowatt hours. So this is a guideline. Okay, so it's expected to further reduce to 362 in 2015. All right, and then when we have the batteries, we will have to maintain it, right? So there will be along the lifespans of your system, there will be some maintenance costs. Okay, just how it was the initial cost. The maintenance cost for battery is relatively affordable, so it's low. So for example, we need to change some coolants for the batteries and then replacing the cell, for examples. So regular maintenance is about $10 per kilowatt per year, or 0.03 cents per kilowatt hours. Okay, so this is considering the lifetime for 10 years for lithium-ion battery. If you look at the lead-acid battery, the price of the O&M is quite similar, but you can see that the lifetime is slower. As we discussed just now, the lead-acid battery has shorter lifespans. And then another interesting one would be the redox flow. At this point, the project cost of redox flow is a lot expensive than the lithium-ion battery. Okay, and the O&M is rather quite similar, but the redox flow can run for longer time, for 15 years. So for more information, you can find from this report, which dated in July 2019. So there are a few other types, for example, pump storage, combustion turbine, the compressed air energy storage, flywheel, ultra capacitors. So these are still in the research and development stage. So you can find the project cost is actually quite high. Okay, so but their lifespan is also quite high as well. Okay, so this is for your reference. All right, so that is the answer for the first questions. So, all right, so maybe we will look at the second questions, which is quite related to the first question. So the question is asking, which energy storage do you think is suitable be used commercially with renewable energy systems? So according to this report in 2020, this is the type of storage being applied as a stationary energy storage. Okay, so you can see that the largest one would be these two, the molten salt storage and the lithium-ion battery. So they contribute the largest part in the share. Okay, and if we look at the trend now, you'll find that the molten salt, the blue one is molten salt, is actually quite high. Back in 2010 to 2013, they start reducing. So the molten salt basically store the energy in the form of thermal energy. So it's usually a very large scale of storage system. We need to have a proper facilities to build it, store the energy, and then to actually convert it back, thermal energy back to the electricity through heat engines. Okay, so it's not as easy to apply as the battery, where we can just buy battery, install, and it is scalable easily. So, and we can see that the lithium-ion battery is actually gaining the market shares, okay, getting market shares. But when we look at the technology analysis, we will see that the molten salt is over here. The technology maturity is still average, okay, and this is the cost. The cost is also average, all right? But you can see that among all these technologies, even the CAES, the compressed air, which gaining a lot of market share right now, it has a good maturities of the technologies. But when we look at the cost, you find that the lithium ion is still the most affordable options, and the compressed air, the cost is still quite high at the moment. All right. So I hope this can answer your questions. The lithium ion is still the good options right now. So another question that is also related to the previous questions would be the suitable power electronics converter in the market for this ESS. So by looking at the previous slide, we know that the batteries, the lead acid battery, the lithium ion batteries are generally popular. It can easily install in any houses, factories, commercial buildings, even grids. So let's look at what are the converters. You know that the battery is in DC, and we need to convert it into AC. So there are actually many inverters, hybrid inverters that can work with different type of battery and PV system. So for example, like Schneider Electrics or ABB and other major manufacturers. So this is the examples that I took from Schneider Electrics, where it has this hybrid inverters. It converts the battery AC to the DC to the AC to supply your house. And then this can also be integrated with your PV systems. Okay, so it will be responsible to taking in your PV generation and charge the battery when it's necessary, and discharge the battery when you need to use the loads. So you can do some settings there. So either you want to do peak load shaving the battery supply when the load demand is high, or to do the grid boosting. So the grid, when you get maximum power from the grid already, you need extra juice, you can just drain from the battery. So this all can be set through all these power inverters in the markets. Okay. So this is questions from you, Dr. Jun. Exploitations of rare earth materials or raw materials of battery to the environmental impacts, and any alternative raw material which is environmental friendly in research or studies.
Thank you, Dr. Chong. Basically, not so many types of rare earth materials being used in the battery, but if the question is referring to the electric car, okay, electric car, of course, there are a lot more rare earth materials being used, particularly for the fabrication of the permanent magnet. For example, lithiumion and praseodymium. So those are the rare earth materials. Battery-wise, the old technology of batteries which we use lead. Okay, so that's one of the not so environmental friendly material. Okay, but there are lots of ways how to recycle it. Okay, rather than dumping into the landfill. So alternative materials has been a quite interesting area for the battery material research. Okay, some of the materials that people are looking right now will be the compound, like the ternary compounds. Okay, they will look at the quaternary compounds. So what does it mean? Compound or elements, for example, hydrogen is one element. So if we have ternary compound, we have three elements being combining together. So why do we need more than two elements for the compounded materials? Simply because this type of materials are able to give us better performance, okay, in terms of the electrode performance, or even in terms of whole battery output, okay, whole battery output performance. All right, so specifically what are the raw materials? So there are lots, okay, that has been researched, okay. So probably we have to look into, I mean, we have to look into the details. If really interested, want to look at the alternative raw materials. All right, Dr. Chong, any next question?
Okay. As the materials to make the storage, such as lithium-ion battery, are also limited and hard to recycle, how could energy storage be more sustainable? So obviously, there are research going on how to use to find out research on the alternative materials for the battery fabrications. Okay, so but this another actually interesting things going on right now is actually the reuse of the retired lithium-ion battery. So we know that we are actually expecting increasing adoption rate of EV, right? So the byproduct of this increasing adoption rates of EVs would be the higher amounts of retired lithium-ion batteries. So this battery, at a certain point of time of the EV, electric vehicles, so they will be removed from the car, from the vehicles, because being that they cannot longer fulfill the range, the drive range for the car. So, but this battery actually they still hold about 70 to 80% of its rated capacity. Okay, so this battery we take up from the car and it still has 70 to 80% of the capacity. We should actually give it a second life, to where we can actually use it as a stationary energy storage systems. Okay, so there are some of this approach going on, so we can actually use the lithium-ion battery to the end of the life, and then we will do the proper recycling process for the energy storage. So on the second part, how practical is it to incorporate biological system in energy storage and renewable energy power system? So maybe you can add on this point, Dr. Chong.
Yeah, thank you, Dr. Chong. Basically, incorporating biological system into either energy storage or renewable energy systems is quite a new thing. It's still at the research mode. Okay. Examples would be the fuel cell. We have seen microbial fuel cell. So, which means the production of the hydrogen, okay, coming from fuel cell is being helped or being carried out by the bacteria. Okay, so we're talking about microbes. In terms of energy storage, integrating microbe, okay, a microbial into battery, still quite new. All right, but again, the downside will be the output density or the performance is rather low. Okay, why is it so low? Because we were talking about a minute scale of the organism, which is microbe. Okay, so still quite new research area. The potential probably will be in the very far future, not in the short term. I can foresee far future probably can be integrated together with the bio devices. Okay, it could be anything as long as it is related to bio. Yeah. So basically, how practical it is, we have to look at how does that innovation come into the picture as time goes on.
Okay.
We have one question sent earlier. The question is like, what are the most reliable hydrogen storage materials? So currently there are three main concepts how to store hydrogen gas. Okay. The usual way will be to store it into the gas cylinder. Okay. We pressurize it and then we store it into the usual cylinder gas tank, like the normal gas tank. Okay. The second type would be we liquefy the hydrogen and we store it in the liquid form. And lastly will be storing it in terms of chemical bonding, or we call it framework storage. Okay, so the framework storage, okay, metal framework storage still rather new in this application, still at the research phase. The most reliable, I would say, would be storing it in the liquid form, okay, because you get more volume, okay, with a lower cost.
Okay, so right, so this is the questions that we collected
So I think we have live question. I think
yes, we have a few. So
I think my questions.
yeah, so hopefully we can.
So let me read the first question. The first question is how do you view the usage of nuclear as new source of energy? Right? Do the nuclear fusion project bring up positive changes? And let me try to answer this. So nuclear fusion, although everyone's, I mean, for the physicists, okay, they know the concept of nuclear fusion, but putting it into commercial application is quite new. Okay, whether it will bring positive changes, yes, of course it will, but we have to look at the environmental impact that that should be contributed by the nuclear fusion waste. All right. So I don't foresee Malaysia will go into this path, but countries like UK, they probably will look into the nuclear fusion, okay, or even the United States, right? So whether it will become the new source of energy, probably part of the alternative source, but I don't think it will come into the mainstream, okay, of the energy source. Do you have anything to add, Dr. Chong?
That's a good answer from you.
Okay.
Okay.
Second question is, can pumping water back into hydroelectric dam be considered a possible energy storage? Theoretically, yes. In fact, the hydro dam is basically a large energy storage, okay, in the form of potential energy. So that potential energy of the content water body, okay, will be used to generate the electricity, okay, inside the hydro dam. Yeah, it's one form of energy storage. Next question is, to integrate ESS to renewables such as PV, current technology has a limited cycle before the efficiency drops. Any research that is currently done to match the PV module life or degradation? Dr. Chong, you want to answer?
To integrate ESS to renewable energy, so current tech has limited cycles and the efficiency drops. Any research that's currently matched to PV modules life? I'm wondering, like, if you're matching module life and degradations. So I assume that you're asking because the ESS has a limited cycles, okay, and the efficiency will drops. So this we can't deny that the ESS, when we, for example, the battery we put in the system, it will degrade over time. So that comes the concept of hybrid energy storage in the research stage, where for my research, I actually integrated supercapacitors to support the battery as a primary storage, and the capacitors to actually reduce the cycle life, the cyclings of the battery, so that we can extend the battery lifespans. Okay, so that is what we do, with the objective to minimize the battery degradations and to maximize, to minimize the life cycle cost of the energy storage systems. So that's the answer. So another question would be, would like to understand the reason of high cost of ramping up for power plant. They have a SCADA or PPC that is built to cater the grid requirements. Yes, actually this is with the operating cost. Okay, so actually by doing this, right, significant things of rapidly ramping up of the power generations, right, it will increase the wear and tears as of the system. Okay, so every time, for example, we need the power plant is on and off the boiler, so they will go through some large thermals and pressure stress, and this kind of processes will actually shorten the component lifespans. Okay, so this is one of the reasons as well, of the reasons. And then the next question, currently Peninsula Malaysia's grid is stable with 0.85 lagging and 0.5 leading. We install a large ESS affect the grid stability in any way? That is actually depending on the grid, the inverters that we are using. As we know that if we install a PV systems in our systems, right? For example, in the factories, so we importing the same amount of the real powers and also the Q, the reactive power from the grid. So when we generate our own energy storage in DC, which is from the PV, so we will inject real power because it's only generate real powers into the system. So the amount of real power that we import from the grid will be reduced. Thus, but the reactive power will still remain the same. This will cause us the impact factor, the power factors to drop. Okay, because the reactive power is still the same, and then the PV generation generates real power, okay, that causes the power factor to drop. Okay, so similarly, if you have a battery, which is a DC source, and then we generate real powers into the grids, okay, so then without generating any reactive power into the system, so it will affect the power factors of the system, the grid as well. So, but now all these inverters, they have the functions to actually produce the reactive power at the same time. So that can help to maintain the power factors of the grids by converting the real power into the grid and also generating some reactive power through the converters. Okay, so for the aim of carbon emissions reduction is massive production of electrochemical battery or storage system will increase the global carbon emissions? Just a curious question. You have anything to say about this, Dr. Jun?
Yeah, earlier on I shared the slides on the number of carbon emission, right? So that should take into the account of the whole supply chain of whatever process that we're talking about. So let's take, for example, the electrochemical battery or any similar storage system. If we start from the supply, okay, and follow the change all the way to the consumer, okay, at every point there will be certain amounts of CO2 being emitted, okay. So we have to look into the overall CO2 emission, okay, right from the beginning to the end consumer. So just remember, before that, when there's no battery being used, okay, the CO2 might be slightly higher, but when we replace it with battery, okay, there will be some reduction of the CO2. No doubt there might be some slightly increase or maybe change in terms of CO2 emission right at the beginning of the supply chain, okay, but by and large there will be some reduction. So what is the number of the reduction? I don't have the figure now, but it'll be interesting to know. But I read somewhere that the CO2 emission will be reduced. Okay, the only problem is to identify each of the process within the supply chain to reduce the CO2 emission. Unfortunately, for battery like lithium-ion battery, we need lithium. So lithium, you need to mine it. So when you do mining, so after you mine, you need to do subsequent process like purification and other chemical-related process. So these processes might somehow contributed to the CO2 emission. So again, it depends on the supplier or the vendor or even the manufacturer, how they can play their roles to reduce CO2 in their process. Okay, so that is what I think.
Okay.
All right, so next question. Can we answer about computational future? I think this answer is repeated in the last question. Okay, a little bit on the future of computational chemistry in determining the suitable energy storage devices. Well, there are two ways of computational chemistry. Basically, one way. So I believe that you are referring to the materials or chemistry computational. So what is the future? Of course, it's very important, especially for the material science research. Before you start off with experimental work, okay, you can start off with the computational chemistry or molecular computation, computational molecular. Okay, the idea is to find out whether that composition or the compound that we would like to explore, does it have the sufficient properties that can be used for the materials for the battery, for example. Yeah, I would say that people are starting to look into the computational theory first before they move on to the experimental work, or even before move on to the prototyping.
Okay.
All right. So then the next question, let me see. Okay, next question is for the aim of carbon emission. Okay, is the massive production of electrochemical battery and PV system will increase the global carbon emission? Yeah, I think I've answered this question just now. It's the most similar. So this depends on the individual process within the whole supply chain. So it also backs to the role of the manufacturer or the vendor. Okay, whether they're willing to reduce the CO2 emission within their processes. Okay, so let's see what's the next question. Okay, I believe the next question is air conditioner can consume lots of energy. In the future, will there be air conditioner that will accept fluctuating power generated from renewable energy such as wind and solar energy? Currently, the commercial air conditioners require inverters and batteries for stable power output. Dr. Chong, I think it's talking about the energy mix that connect back to the main grid, right?
I think the question is asking about is there any PV powered air conditioners in the future?
Oh, okay.
So yes, the air conditioners requires a lot of energies. So it probably takes about 1.5, 1.8 kilowatts for it to run. So actually, in order to create a PV powered air conditioners, you will need, let's say for example, the PV powered, right? So you will need quite a lot of PV panels. Okay, let's say your air conditioners takes 2 kilowatts, you will need to have 2 kilowatts of PV panels, and then the sun has to shine as the STC conditions. So we did get 1,000 watt per meter square from the sun, so which is quite difficult. So you will need to have at least upscales your PV size. By looking at the PV technology right now, is quite challenging because the PV will be quite huge if you want to power a PV air conditioners. So, but if the PV efficiency, like what Dr. Chong presented, can improve to a very high level, so you can have a smaller size of PV panels to power the PV the air conditioners. Okay, so I would my concerns would be the size of the renewable sources to power a load like PV air conditioners.
Yeah, I think you still need a batteries as a backup.
Yes. So, hi, Dr. Chong.
We have the last. Okay, I think two more questions. I think two last questions.
Okay.
So, there's one audience would like to know if our research also look into thermal management of the energy storage system. For my case, I'm not looking at the thermal management, but I'm looking at the thermal conversion. Okay, I'm not sure about you, Dr. Chong.
Okay. So for my research, I actually look into the degradations of the energy storage systems. So to me, at this stage, I'm looking into the temperature effects. So for the management parts, I have not get into it, but I definitely will look into that in the futures. So as now I'm still studying the degradation mechanisms of the storage.
Okay. Next question. This is the second last question. What are the plans to improve renewable energy in terms of efficiency, reliability, and high cost of installation? All right. So I'm not sure which renewable energy that the audience is asking. Well, maybe we can pick one examples. Maybe PV. Right. So if you're talking about the PV, how can we improve in terms of efficiency, reliability, and the cost of installation? So of course, the main cost is coming from the materials, and then the manufacturing cost. So of course, how to drive this cost down? We have to come up. I mean, the researcher or even the private companies. Okay, they need to look at the materials that are able to produce, okay, in a huge quantity, but yet at a lower cost, and at the same time able to give better performance, okay, when used as a PV materials, okay. So this goes all in all with the reliability, okay, as well as the installation. Anything to add from you, Dr. Chong?
I think that's good. So we'd like to ask Dr. Jun and Dr. Chong, what are your opinions on the goal set RMK 12 with all the material costs is increasing? Yes, a serious issue such as silicon, rare earth materials, and etc. So it is going to be, I would say, challenging, because if you look at the economics right now of the world, raw material price increasing is a very serious issue. So even now, China has to do some power controls, right, for certain cities, because one of the reasons being that the coal is so expensive. If the generation actually, the power producer generate a kilowatt hours of energy, they're actually making losses instead of making profits. So also in the UK, quite a lot of utility service providers actually collapse because of the high material costs as well. So this will definitely impact the goal set. So any opinion from you, Dr. Jones, about our RMK trial, considering all these factors?
Yeah, knowing that the material cost will increase, but also have to look at the next 5 years, the government budget. If the budget will be increased, I think this budget will be able to cover some of the material costs. But again, I think government is adopting a different kind of approach. Okay, they will not, like they probably will pair up with a private entity, okay, to share the cost. All right. So, I mean, that's what the government is working on at the moment to reduce the cost overall. Yeah. So and then whether the goal sets in the RMK 12 is it able to achieve, time will tell. Okay. I believe to achieve the target of 25% of energy mix by 2025 is possible. 31% is a challenge. Yeah. I think we have one more last question. Oh, okay, actually 2 questions. One just popped in. Does artificial sun has the potential to replace as the main sources of the energy provider of the world? All right. Not sure that your understanding of artificial sun is same as mine. Artificial sun usually is used in Northern Europe when they have long winter time. Okay, and they basically use a mirror, a giant mirror to reflect the sunlight, right, to the ground. All right. So the Northern Europe, they need this because of the geographical geographical factor of certain particular town or area that has not received much sunlight throughout the year. Okay, so this artificial sunlight is beneficial, okay, at a certain point, but whether it can be the main source of energy provider, probably not if you look at the overall total world population, okay, or even the entire countries, right? Anything to add from you, Dr. Chong?
That's good. That's good. So maybe we look at the final questions.
Yeah.
So what is your viewpoints on the reuse of lithium-ion battery as BESS viable in industrial applications? Okay, economics for implementations wise. So reuse lithium-ion battery. So the first challenge of this application of reuse lithium-ion battery would be, first we need to have the disposed lithium battery still in a good conditions. So in order to implement this, we need to have certain facilities, some agency or companies that can do the checkings of the battery health before we can implement them into the systems. Another issue would be the retired lithium-ion battery from the EV is a good source for the second life batteries, because most of them are still in quite okay conditions. But the problem we are facing right now is that the adoption rates of EV in Malaysia is still very, very low. So I believe in Thailand, they have ambitious plans to convert all cars into EVs in 2030 or 2040. And our Malaysia is planned to convert them in 2050. So this is another challenge. We do not have large supply of the second-hand the disposed battery as well. So, and in terms of their industrial applications, so if I'm thinking about industrial application, the most important one would be the backup supply of electricity, okay, which I think that the lithium second-life battery could be a good candidate for that, because you can just charge it and you don't need to cycle it most of the time if you use the backup electricities generations. So another application would be to reduce the maximum demands, as most of the industrial player facing right now. So if we can have a good supply of the second life batteries, and we have a good flows of how we can test it and then reassemble it and then put it into the systems, and then we can actually produce some low cost and stationary energy source system for industrial to minimize the peak usage during the peak periods. So this could be quite beneficial for industrial players, because the MD is quite high and the battery, we need to have low cost battery. So this could be one of the solutions, but things will happen in maybe coming decades. So we are currently looking at the research how to set up the whole ecosystem of this one as well. So I think this is the last questions.
Yeah, I think no more question.
No more questions. So all right, so that would be the end of this webinar. So thank you everyone. So I'm glad to see that there's some of the audience coming from industry. So if you have any industry collaboration that we can do together with the university, please feel free to contact me or Dr. Jones, so we can work together to create a better future for our coming generations. Thank you everyone.
Yeah, thank you everyone for spending 1 hour plus time. Okay, thank you.
Right.
All right, so we will end here. So all the best everyone. Stay safe. Yeah.
Stay safe. Bye.